Hello, I'm Joshua Jennings. I'm a senior civil engineering student at Florida Gulf Coast University. I'm presenting the failure of the New Orleans Hurricane Protection System due to Hurricane Katrina. This presentation is part of the semester specialization requirement for Geotechnical Engineering 2. Hurricane Katrina made its landfall in Louisiana on August 29, 2005. When it made landfall in Louisiana, Hurricane Katrina was a Category 3 hurricane, meaning that the wind speeds were between 111 and 129 miles per hour. Hurricane Katrina caused over 1,100 deaths and caused over $100 billion in damage. The storm itself did not cause as much damage compared to its aftermath, which was catastrophic. The failures of the levees and flood walls flooded 80% of New Orleans with deaths of over 10 feet. The Hurricane Protection System protects the city from floodwaters of the Mississippi River and Lake Pontchartrain, both of which are connected to the Gulf of Mexico. Construction of the system began in 1965. The entire system is about 350 miles in length. The system has 58 miles of flood walls, 56 miles of which are eye walls, and only 2 miles are T-walls. The rest of the system is made up of earthen levees. The federal government owns 284 miles of the system, and the rest is non-federal. The non-federal sections are owned by local government and other municipalities. The elevation of the system varies from 12 to 15 feet above mean sea level. A levee is defined as an earthen embankment built with the purpose of controlling water. The levees around New Orleans make up 292 miles of the hurricane protection system, so a vast majority of it. The top of the levees reach an elevation of 12 feet above mean sea level and is 10 feet wide at the top. The compacted material in the center does not exceed a 3-to-1 slope, and the uncompacted material on either side does not exceed a 20-to-1 slope. The New Orleans levees failed primarily due to erosion caused by overtopping. Once the water started rushing over the top of the embankment, the soil was quickly displaced. The erodibility of the soils used in the levees ranged from low to very high. This variability was not taken into account during the design process, and the water seepage through the levee decreased the amount of shear stress the soil could withstand, thus leading to an increased rate of erosion. In the past, some levees needed to be raised to a higher elevation. However, there were already businesses and communities built at the bases of these levees, so increasing the footprint was not an option. The solution was to build an eye wall, which is basically a sheet pile in the middle of a levee. The top of the sheet pile is at least 12 feet above mean sea level, and the bottom is at least 20 feet below mean sea level into the ground. But unfortunately, it turns out sheet piles weren't high enough in some areas and weren't deep enough in other areas, and in some areas not high or deep enough. The eye walls, much like the levees, were severely under design. Engineers failed to recognize the soil variability under the eye walls and did not design for an acceptable factor of safety. When the rising waters pushed on the back of the eye walls, a gap began to form. This gap caused a decreased seepage path and decreased the shearing resistance of the soil because the slip surface stopped at the gap rather than through the entire embankment. Some of the eye walls were not pushed over, but rather slid on a weak layer of organic material. This was the stability failure through foundation clay. The eye wall and the embankment were just pushed out of the way, and the area was allowed to flood. Under seepage of water caused both erosion under the eye wall, leading to less support, and uplift due to poor water pressure. The last type of failure is the most obvious. When the water overtops the eye wall, it's basically a waterfall, and it leads to a high amount of erosion on the protected side of the eye wall. This removes the material and allows the water to push it over a lot easier. This is the 17th Street Canal Breach. It's a good example of the stability failure through the foundation clay, where the walls and the embankment were just sort of pushed out of the way. Notice the pieces of wall and the levee chunks. They were just pushed, and that dotted line is where the levee should be. And then you see the arrow towards the left of that where it is now, or was. T-walls were built for similar reasons as I-walls. The difference is that T-walls have a footing and additional pilings that extend into the ground at an angle. No T-walls failed. But there were only 2 miles of them, so they didn't do a whole lot of good. So what went wrong? Why did the system fail? There are many reasons why they failed, but one of the main reasons they failed is that they were way under designed. Risk and reliability were not taken into account. Rather than using the T-year storm, design engineers used the storm of record, and that was much weaker than Hurricane Katrina. Variability was not taken into account either. The levees and I-walls had a lot of variability, and that's one of the main reasons why they failed. There was also no redundancy. If one levee or flood wall was breached, the entire area was flooded. The entire city of New Orleans. There were no emergency precautions designed in the event of a failure. And the levees and flood walls were also just poorly maintained. There were multiple agencies involved in the maintenance of the levees and flood walls. Each passed the buck on to the other agencies because of budget cuts and confusion on who was actually in charge. Bureaucracy in the United States. Engineers abide by a code of ethics. The first and foremost one is that engineers shall hold paramount the safety, health, and welfare of the public, and shall strive to comply with the principles of sustainable development in the performance of their professional duties. The engineers violated this ethic, mostly that first part. The levees and flood walls were severely under-designed and led to the most costly natural disaster in U.S. history, as well as very high loss of lives, one of the worst engineering failures in U.S. history. But by studying disasters like these, we as aspiring engineers can learn how to avoid these kind of disasters and appreciate the consequences of fulfilling our responsibilities. Thank you for watching.